Having seen deterministic finite automaton and couple of interesting properties, let's explore some more properties about DFA. So in particular, let's look at this automaton. So you start from Q0 and read A and reach this final state. Then when we read a B, we continue to stay here. We may read a couple of more A's over here. When we read a B, we come back. So we see that it accepts A, it accepts B star followed by A, or A followed by A star. So clearly we see that it accepts all strings ending with A, or it may so happen that it reads B star, and this pattern can repeat A star followed by B and followed by B star. This pattern can repeat any number of times followed by A star. So you get to see that B star followed by A star, B star, again A star, B star. So this can happen any number of times. Finally you get to read A and A star. Fine, so you still see that it ends with A. So this is, in some sense, we know there is a succinct way of expressing the language accepted by this automaton. We call this as regular expression. The underlying set becomes regular sets. So when we talk about properties of deterministic finite automaton, which means we are discussing properties of deterministic finite automaton or properties of regular sets. So by observing the properties of regular sets, we discovered something called pumping lemma. With that we were able to show that certain languages are not regular. Fine, we gave an interesting counting argument. With that we showed there are non-regular languages, and how do we show some of them are not regular, and that we did using pumping lemma. So now I am going to define a relation. So to talk about a relation, in particular a binary relation, we need a domain. Domain as universe of discourse or the underlying set. This is called universe of discourse. You must have seen this in discrete structures course. So the domain is sigma star. So with respect to this sigma star, we are going to define a binary relation, which means relating two strings in sigma star. You take some two strings. Now we tell how these two strings are related. Okay. So what we do is the following. Look at this automaton. Delta of q0 comma x, if it is same as delta of q0 comma y. Okay. If this is true, then we say the strings x and y are related. Okay. So x related to y if and only if delta of q0 comma x equals delta of q naught comma y. So there may be many pairs x comma y and all of them will be related here, and y can be same as x. Okay, so y is a string, x is a string. So where do x and y come from? X and y belongs to sigma star. So you take any two strings and you see that delta of q naught comma x is same as delta of q naught comma y, then you say x and y are related. Fine? Okay. So what is this telling us? This is telling us that you look at this value and this represents a state, right? You look at delta of, now it is a string, okay? So I carefully use this notation. So delta cap of say q naught comma, let me take say BA. If you take BA, output is Q1. And delta cap of say q naught comma, let me take BB. If you take BB, output is q naught. That shows that BA is not related to BB. So delta cap of q naught comma BAA is Q1, and delta cap of q naught comma AAA is Q1, which means BAA is related to AAA. Fine? So what are we saying? Look at any two strings in sigma star and look at this. If delta of q naught comma x is same as delta of q naught comma y, then those two strings are related. For example, BA and BB, for BA output is Q1 and for BB output is Q naught. Therefore, these two strings are not related. But for BAA and A followed by AA, you see that the output states are same. Therefore, these two strings are related. So if you carefully look at this, so q naught comma x, the value of this, it can be either q naught or q1 because it is a state in this, correct? So which means you say that x related to y if for all x comma y delta cap of q naught comma x is same as delta cap of q naught comma y, which is same as q naught, or delta cap of q naught comma x is same as delta of q naught comma y, whose value is q1. Correct? So which means these two are related when if the output state is q naught or the output state for both of them is q1. Okay. So now what is this telling us? You look at sigma star. Sigma star can be partitioned into two sets. All those xy such that this property is true. Delta of q naught comma x is same as q naught comma y and the value is q naught, all those x comma y such that delta cap of q naught comma x is same as q naught comma y, and that value is q1. Okay, so which means for all those x the output state is q naught, and for all those xy the output state is q1, and it precisely partitions. So these two are partitions of sigma star. What is a partition? The intersection is empty. The union gives me sigma star. It cannot be the case that an xy that appears here, it is also appearing here. That's not possible, because for this xy, if the output is q naught, it can appear only here, not here. And most importantly, having brought this partition and so on, let's look at something interesting. We see that this relation is an equivalence relation. If x and y are same, we see that x is related to x because delta of q naught comma x is same as delta of q naught comma x. So x is related to x, and if x is related to y, implies that y is related to x. If delta of q naught comma x is same as q naught comma y, which means q naught comma y is same as q naught comma x, which means this tells you it is reflexive, this tells you it is symmetric. We also see that if x is related to y and y is related to z, implies that x is related to z. If the output state is same for xy and yz, so naturally for x and z the output state must be same. If for this it is q naught, for this it is q naught, then for this and this it must be q naught. Or for this it is q1, for this it is q1, then it must be the case that for these two it must be q1. So that shows that it satisfies transitivity property as well. So now with this we see that the relation that we have defined is an equivalence relation with respect to the set sigma star. And we know that for an equivalence relation, one can come up with the set of equivalence classes. We know that the set of equivalence classes partitions the underlying set, in this case sigma star. So the set of equivalence classes partitions sigma star. Okay. Now, what are our equivalence classes? It is this and this. One says it is all those xy such that if you look at the output state for both of them, it is q naught, and I am talking with respect to this example. And the next one says you find those xy for which the output state is q1. So now this clearly tells you that this is one equivalence class, this is another equivalence class. In particular, what is this telling us? This is a state in this is also a state in this. Now you look at it this way. starting from Q0, you operate a string. Okay, you operate a pair of strings x and y, and relation says their output value must be same. So if you operate either they stay in Q0 or they stay in Q1. In general, if there are Q states, then when you operate, it may be in the first state or second state or third state and so on up to nth state. Which means for each state we get one equivalence class. Okay. So we see that equivalence class corresponding to Q0. This is an equivalence class corresponding to Q1. Which means for each Q belonging to this, there exists one equivalence class. Correctly, yeah? Because when you start from Q0, the x can end in Q0 itself, or x can end in Q1, or x can end in Q2, Q3 and so on. Which means the sigma star is partitioned into equivalence classes of this type. So what are we saying? Look at the underlying set sigma star. This is partitioned into two equivalence classes. So sigma star is E1 and E2, and E1 and E2 are equivalence classes with respect to the relation we have defined. So what is E1? E1 consists of set of x belonging to sigma star, and delta of Q0 comma x is Q0. When you say all those x comma y, which means it is a set, right? Which means here is a definition. Similarly, E2 says it is all those x such that x belonging to sigma star and delta of Q0 comma x is Q1. When we say all those x comma y such that their output value is Q1, which means it is precisely this set. Now we clearly see that you take any x from sigma star. When you operate starting from this, you get to see that you will end in Q0 or in Q1. Therefore, it will either appear, the x will either appear in x1, E1 or E2. So you connect with the automaton. So informally, if you describe this, what will be the description for x? Formally we say it is all those x such that the output state is Q0, which means if you look at this sigma star, you can divide sigma star. Sigma star contains all strings over a comma b. So all strings over a comma b, you can see it this way: strings ending with the symbol A, or strings ending with the symbol B. Correct? So if you look at any string, the other one is of course epsilon. So it will be A, or strings ending with B, it will be B, or maybe A plus B whole star followed by B. So any string will be of this type, right? A plus B whole star followed by A, or A plus B whole star followed by B, or just epsilon. And if it is epsilon, then we know that Q naught comma epsilon is Q naught. So epsilon is covered here. Now look at these two components. If it is ending with A, then it is Q1. If it is ending with B, suppose X is, for example, look at B, B, A, B. Then you clearly see that you operate B twice followed by A, this. So any X that stops here, it has this pattern, right? It ends with B. Any X that stops at Q1, it has this pattern, it ends with this. Which means this one is a set of strings ending with A or epsilon. This one set of strings ending with okay, this one is B and this one is A. So this consists of all those strings ending with B or epsilon. Q1 is all those strings ending with A. So we see that sigma star is clearly partitioned into two equivalence classes. No string is left out. So this is what we were saying. One can define a nice relation on sigma star and then bring out something called equivalence classes to understand the underlying set.